Alright, on our homework number 11 we have x cubed minus 1 over x cubed dx. And ultimately if we recognize these as power functions, x cubed minus x to the negative 3 dx, then if we use the power rule, we'd get x to the 4th over 4 for that part. And then this part would be x to the negative 2 over negative 2. And simplifying, we'd have a minus minus situation, so it would wind up being plus, so it would be x to the 4th over 4 plus, and then it would be 1 over 2x squared on the bottom, plus c. So already a 2 on the bottom, the x would go down to the bottom, make it a positive power. And that would do it. Questions on this one before we move on? And 17, we have integral from 2 over x minus 1 plus x dx. So recognizing here that if we were to rewrite this as a power function, it would be x to the negative 1, which would indicate that it's a natural log problem. The other thing we can recognize is we have a 2 here, which is a constant multiple. So if we wanted to rewrite this integral altogether and separate the two parts, certainly do that. And keep in mind here, as long as the derivative of this is 1, then we don't have any chain rule issues. So ultimately this would be 2 natural log of x minus 1 and x minus 1, that is, absolute value. And then ln absolute value of x plus c. That's it. Questions on that one? What else? 23, we have the tangent squared d theta. And ultimately, we don't have an antiderivative for that, essentially. True? Alright. So the question is there a way that I can rewrite that integrand so that maybe it's something that we could find an antiderivative for? It would be sine squared over cosine squared, that's true. Let's try that, because that would be one thing that could be done, of course. So if we wrote it as sine squared over cosine squared, and then that ultimately wouldn't do us much good, because that's certainly not a known derivative either. However, if we maybe try the two hints that they gave us in 21 and 22, maybe we could replace the sine squared and cosine squared with those. Let's try, right? So let's try, see if anything good happens. So the sine squared, they told us, is 1 minus cosine 2x over 2. And then the cosine squared is 1 plus cosine 2x all over 2. Alright, and with that, we if we flip and multiply here, we're going to wind up with 1 minus cosine 2x over 1 plus cosine 2x. So, definitely not. So, alright, so bottom line here is, did that do us any good? I mean, ultimately we're still at a point where we have something that's still not a known derivative. True? And we can't split it up. We don't have a quotient rule. We can just do the top and the bottom separately. That's definitely not one of our rules that we have. If it was an addition, we could certainly, but this is being a division. Okay, means that that's not going to work. Okay. All right. So then the question would be then: is there anything else that we might be able to do here that we could get something in the integrand here that would be more useful? So like I said, with this particular integrand, that doesn't put us at anywhere that's any better than what we already had. If you look in your notes that I gave you, there are some trig identities in there that we might be able to employ possibly. The notes I gave you from your syllabus. So why don't you grab those and get them out and see if there's anything else we might be able to use. At this point, you know, again, we used the two identities they gave us to simplify the sine squared and cosine squared into this stuff. But the question is with this not being anything that's useful to us, what about cosine of 2x? We have some formulas for cosine double angle, don't we? Formulas for double angle cosine. Cosine of 2x equals should be three different things. Let's just say for argument's sake that we tried that one here in the top. So 1 minus cosine squared x, right? Yeah. Okay, that's our double angle. There's three of them, remember, that's one of them. One thing that would be good about that is that if we subtracted here, we'd get the 1's to cancel out, and we'd be left with positive cosine squared x, wouldn't we? So that would be on the top. I don't know why I changed from theta to x here, bottom line, but either way. If we put that in the other one, if we did 1 plus that, we'd end up with 2, and then minus cosine squared x, which ultimately wouldn't do us much good either. The other formulas in there are changing the cosine into sine, which really, if we had this in terms of sine, would we be any different both? No. All right. Then those double angle formulas, essentially, you know, we could try some different combinations, but they're not going to work either. So what else do we know about these trig functions? What other identities do we have in terms of, maybe go back even to the original statement here, tangent squared theta. Ultimately, at this point, if it's not a known derivative, there's got to be something we can do with that integral to get it so it is. So look at your list here. Is there anything about tangent squared that we can do with? We know there's an identity that has to do with sine squared and cosine squared. Is there one for tangent squared? What if we wrote that as secant squared theta minus 1? Ultimately, what do we have now? Isn't this a known derivative? So if we rewrite that as secant squared d theta minus 1 d theta, split those two up, this would ultimately be tangent theta. This would be theta. Put plus c on the end, we're done. So again, what we're trying to do here is we're trying to develop some strategies here to essentially find the antiderivative for any function that we're given. First and simplest strategy is it a known derivative? If it is, then you can just anti-differentiate because you know the function that it came from. If you don't know the function that it came from, is there any way we can manipulate the integrand so that it becomes a known derivative? Okay? And a lot of times that's going to be the case when we have trig functions, because trig functions, there's lots of identities for trig functions, and if it's not one, it's not an obvious antiderivative, then we can replace it with something that it might be equal to, and maybe the stuff it's equal to is going to be something we can anti-differentiate. Okay? All right. So in review, our two strategies at this point for finding antiderivatives are to recognize it as a known derivative, okay? Which means we can use our formulas that we have in our list and our derivative formulas that we learned earlier, okay, to find the antiderivative. Okay? Or we can try to manipulate the integrand somehow, do some algebra or some trigonometry, and put it in a different form. Because again, what we change it to is exactly the same thing we started with, it's just in a different form. And in the different form, we found that the two parts are integrable. Okay? Alright. So bottom line here is this something that we maybe would try? Yeah, sure. Okay? But we tried it, and what happened? Didn't work, so we need to find something else. Okay? So we'll go back and start again and look at tangent squared. Is there anything else we can do with tangent squared? Certainly. There's another identity that tangent squared itself is equal to. And we don't have to do that sine and cosine business. Questions on that one? All right. I want you to look at next here then is I gave you a packet here. Let's find that packet that I just gave you today. just to give you an overview, it talks about this on the front page here. I would take the time to read this about slope fields because this is something that's new for us, is what in the world is a slope field. The bottom line here is this. If we were going to try to find an antiderivative, say for this tangent squared x function that we just studied here, we were able to do that with algebra. We were able to find a function whose derivative is secant squared or tangent squared x. Okay, we were able to do it. Is that always going to be the case? Not necessarily. And so ultimately, what happens in life is this: if we have some data that's collected, and the data is rate data, okay, which ultimately means that if we were to graph the rate data, right, it would give us a function that's a rate function. True? And so ultimately, that rate function, being a rate, is a derivative. True? And so we might have a function that we know that can be modeled by dy dx equals, let's say, x squared plus 2, just for argument's sake. Okay? But again, this is our rate function. It's not the function y that this came from. Okay? It's the rate function. This is a description of the rate. Because sometimes when we collect data, okay, it's rate data. We might not have data about the actual relationship between x and y, but we have the relationship between x and the rate. Okay? If that's the case, then we have what we call a differential equation. Okay? So ultimately, any equation that involves a derivative is a differential equation. And so part of our focus here at this point is to use what we've learned so far and what we're going to learn from here on out in this chapter to solve differential equations. Now, here's the good news. The good news is that some differential equations are going to be relatively easy to solve. Like in this particular case, I would have x cubed over 3 plus 2x plus c. Okay? That right there would be the y that derivative came from. Agreed? Okay. If I were to differentiate y, I'd get dy dx over here, and I'd get x squared plus 2x. C would give us 0. So that would be the antiderivative of this. This would be the solution to that differential equation. Now, the issues that we have, though, are this, is that sometimes the differential equation we're given is not going to be something we can integrate. Okay? There's going to be some that we can, some that we can't. Okay? And the ones that we're going to look at that we can actually solve using algebra and calculus, we're going to look at those more tomorrow. So we'll spend a little more time on this tomorrow. But bottom line is, there's going to be some that we can do what we just did with, and there's going to be some that we can't. Okay? And the ones that we can't, that's what we're going to look at next. What if we can't find a solution for the differential equation given? Well, that brings us to, there's two methods here. The first is slope fields. We're not going to, the other method we're not going to deal with until second semester calculus, which you'll either take next year or in college. But the first method is slope fields, and the slope field tells us this. Okay, what we're going to do is I'm going to draw a slope field for this particular equation. Even though we know the answer to it already, and we can find it with algebra. Okay, let's just say for argument's sake that we couldn't find it. So how do we draw a slope field for this? And then when we draw the slope field, what in the world does it mean? Okay, what is it telling us? All right, so let's see what we're going to do here. We're going to take each point, and I'm going to do just whole number points only. And I'm going to start with 0, 0. I'm going to start with the origin. If I were to put 0, 0 into this differential equation, what would I get? Notice it doesn't depend on y. True? So does it really matter what y is here? No. It's going to give me 2 every time. So if x is 0, I'm going to get 2. What I'm going to do is I'm going to draw, at that point, I'm going to draw a small segment that has a slope of 2. Now, this doesn't have to be an exact science. We're just going to get approximately 2 for the slope. Okay? Now, what if I did 0, 1? What's the slope going to be at 0, 1? 2. How about at that point, 0, 2? 2. What about at 0, negative 1? 2. 0, negative 2? 2. Alright? So again, all I've done is just drawn segments at those points that have a slope of 2. Now, was there any science behind me making a slope of 2 there? No. You know it's 2 because it's positive. Okay? And it looks like it's a little steeper than what 1 would be, which is at a 45-degree angle, essentially. Okay? So if I had to draw between 2 and 3, if the next one, if I moved over to the right and I had to draw one that's 3, I'm just going to make that a little what? A little steeper than the previous ones I drew. And that's exactly what I'm going to do at these 1 points, because if I go 1, 0, or 1, 1, or 1, 2, or 1, negative 1, or 1, negative 2, my x value is going to be 1, which means my slopes are going to be 3. So what I'm going to do at these points is I'm going to draw it just a little bit steeper. And again, it's fairly inexact, but when we get down, we'll have a pretty good idea. And then finally, when we do, I'm just going to go out to 2 in this case, and then I'm going to go backwards to negative 2 in a minute. Bottom line here is I'm going to get, at those points with the x value of 2, I'm going to get a slope of 4 plus 2, which is 6. So these are going to be quite steep compared to the other ones that we're going to do. And again, as long as they are reasonable, you're good. Fair enough? Now, if we go backwards, what's going to happen if we get these points where we have -1 and -2 for our x? Well, -1 in there is going to give us -1 squared, which is 1, plus 2 is going to give us 3 again. So they're going to be a little bit steeper than the ones that I drew here in the middle. And then I'm going to get 6 again when I do these, so they're going to be steeper yet. And so ultimately that would be a picture of my slope field here. Now, bottom line is, what that's giving us here is it's giving us a picture of the general pattern of what the curve y would look like. Okay? Because when we draw the slopes, remember the derivative here, we're drawing essentially a picture of the function from the derivative. Okay? Because this is how our function behaves at certain points. It behaves like this slope. And so if we were to draw it, okay, yeah, that would be that. And so ultimately, keep in mind that if we knew that our actual function y went through 0, 0, let's say right here, that means at 0, 0 it's going through with a slope at 2, okay, and then the slope is getting what? It's getting steeper, isn't it? Okay. And as I go away from this point, my slope is getting what? Steeper again. And so that might be a picture of a possible solution curve. Okay. And is it surprising that it has that shape? Because what is our solution curve? It's a cubic, isn't it? True? Okay. And the other thing, too, is that, remember, I said it goes through 0, 0. Couldn't it also maybe go through 0, 1 possibly and have the same general shape, but go through 0, 1, be up or down from where it is? Which ultimately we know it can be anything up or down because of the plus c part. All right, so ultimately what does the slope field do? It gives us a picture of the general solutions to this differential equation. Fair enough? Okay. Now, why would that be important for us? Well, bottom line is, when we have data and we're able to write an equation that's y in terms of x, we can use that equation to make predictions. True? Okay. But if we don't have an equation, then how can we make the predictions? Can't, can we? But what does this do for us? If we knew that it went through 0, 0, and we knew that this was our curve right here, okay, even if we don't have an equation for it, couldn't we make predictions with it? Couldn't we find x equals 1 and see what the y values are like? X equals 2, see what the y values are like? Okay. And again, would it be an exact science? No. It would be an estimate from what you drew, but ultimately wouldn't it be better than nothing? And at least we'd have a pretty good indication of what that curve would look like. Even if we can't find an equation for it, we could see the general shape, which is good. Because ultimately if we can draw the general shape, then we can use that picture to make predictions. Instead of putting a x in and finding y, okay, we can look at the picture and see what is y when x is a certain number. Okay? And again, it's an important topic because ultimately, like I said, in this particular case, we can certainly just find the answer with algebra and calculus. But that's not going to be the case in all cases. We're not going to be able to find necessarily an algebraic definition for y in terms of x. Okay? We might be able to, but we might not. Right? And ultimately, this whole topic of differential equations is a pretty vast topic. We're just going to do part of it, which ultimately ends up being the easy part. If you continue taking math and calculus, there's an entire semester class on just differential equations, on just solving different types of differential equations. Like I said, we're going to look at essentially the simplest type starting tomorrow, and then we'll go from there. But bottom line is this slope field business is something that we're going to do if we can't find an actual solution. So here's what I want you to do. I want you to go ahead and turn the page here to find the page that looks like this, where it says slope fields. Okay. So you're in your homework assignment, you have a couple, like 3 more problems to do, I think, from there. But then I want you also to work on the slope field worksheet. On this page, we're going to do exactly what I just showed you. On the given points, you have this many dots on here, and for each of those points, what you're going to go do is go through and fill in your segments. So what kind of segments am I going to draw? On this one, I have x plus 1 as my I have x plus 1 as my differential equation. So if I were to put a 0 in there, I'd get all slopes of what? I'd get all 1 slopes. And then I'm going to have 2 slopes and 3 slopes and so far as I go out. And then going the other way, what are the slopes going to be like here at this point right here? Where we have x equals -1. the slopes are going to be 0. So keep in mind, if I were to draw a point like that, would my slope be this? Would my slope segments be that? True? Okay, so going down that line, we'd have slopes of 0. So we draw horizontal segments on all those points. Yeah.
So we can write on these?
No. So do not write on these. Anything in the black book, don't. So you're going to just make it on a different piece of paper. Okay. Ultimately, here you're going to see some patterns here which will develop. You'll see it as you do it. But bottom line is this one is only defined in terms of y. So in other words, at each of these points, let's say I take the point 2, 1. Okay, is the 2 going to have any bearing in this equation? There's no place to put the 2, is there? Ultimately, we're just going to put a 1 in there, and we're going to get a slope, and make that slope at that point. Some differential equations have both x and y, so this means that at each point, whatever point it is, if it's 3, 5, then what's your slope? 8. You're going to draw at 3, 5, you're going to draw a slope of 8. So you're going to draw a little segment that has a slope of 8, and you're good. In this case, we don't have 3, 5 on the picture, so you don't need to do 3, 5, but just the points that are dotted. Okay. Questions so far? Done?
If the slope is negative, you draw the dash the other way.
Absolutely negative. Yep. Just draw it the other way. Okay. So if it's -1, we just draw a -1 slope, -2, whatever the case may be. Okay. Draw it as such. All right. Go ahead and turn over to the next page. Make sure we're clear on the directions here for the rest of these. And again, don't write on here. Write it on your paper. This time we're going to match each slope field, okay, with the equation it could represent. So notice that we have the slope fields drawn here, and then on the bottom we have the actual equations here. Okay, keep that in mind. These aren't the differential equations that would give us those slopes. Okay, these are a picture of the general form, general solution, which these are the general solutions. Okay, so just for instance, if you will, if we take let's say y equals x. Okay, which one would match up with y equals x? Well, y equals x, keep in mind, as a general solution would be y equals x plus c. True? So which one of these pictures here looks like a line with a slope of 1 that goes through either the origin or some other y value? Okay, would it be this one? Okay, so the general shapes of these equations should match up with the general shapes of your graphs that you're trying to identify here. Okay. All right, and then the next part, you're doing essentially the opposite. They give you differential equations this time, and you notice that I gave you the answers on here because I want you to see the patterns. Okay, so the answers are there, but I want you to take a look at these and see why those are the answers. Okay, all right, and then the same thing on this one. They've given you the slope field, okay, and they've asked you to draw the general solution. Okay, notice that 0, 1. If we plot 0, 1, the general shape of the curve is this. If we did 0, -1 down here, wouldn't the general shape be something like this instead? Okay, so same thing on that one. And then the rest of this, what I want you to do with it is I've given you some AP problems that involve slope fields. And they not only have the problem, but they also have the solutions here. And so what I want you to do for tomorrow is just look at the slope field part of it only. Okay, the other parts we're going to leave alone for the time being. So I want you to look at the slope field problem and see what did they ask us about in terms of finding a slope field. Ultimately, it's pretty much the same thing we did in our first part here. So there's a few problems here that are AP problems that have slope field parts to them. This one has the slope field given, and you have to write the general solution. So take a look at their answers. Okay? There's really nothing you have to do per se, but just I want you to look at those problems and look at their answers. All right, and then once you get to this page where it says section 6.2 and 6.3, then what? Stop, because you're done. Okay. All right. So